In this lab, we observed the gravitational force acting on a star as it orbited around a black hole for a certain amount of time. Using these observations, we could then figure out the mass of the black hole. The main equation that we could use to figure out this is the gravitational force equation, which is equal to the constant g times the mass of the star times the mass of the black hole, and divided by the distance between these two squared. We could then solve for the mass of the black hole. After we did this, I found the mass of the black hole to be 3.1725 times 10 to the 31st kilograms. Since the star is moving in a circular motion, we must understand that there are two components of the gravitational force acting on the star, one that is parallel to the tangent of the star's path and one that is perpendicular to the tangent of its path. F net parallel, which is equal to dp dt parallel, or the rate of change of momentum in the parallel direction, accounts for the change in speed of the object, while dp dt perpendicular, or the rate of change of momentum in the perpendicular direction, accounts for the change in direction of the star. This is also equal to F net perpendicular, which equals mv squared over r. By adding these two components together, we can get the total net force acting on the star, which in this case is the gravitational force from the black hole. Using the positions of the star and black hole, as well as the mass of the star, we can run the Python code to obtain a model of the star's motion and the gravitational force acting on it, as well as the mass of the black hole. We must first input the necessary constants such as the mass of the star, the constant g, and the position of the black hole. We can then use our knowledge of the relationship between momentum and force to calculate the gravitational force acting on the star. First, we can see that the initial momentum is equal to the mass of the star times the initial velocity, which we get from p equals mv. We can also find the change in v, which is equal to v final minus v initial, as well as the change in p. We can then calculate dp dt by dividing the change in p by the change in t and setting this value equal to F net, since we know that these two values are the same. We can then find the magnitude of dp dt by dividing the magnitude of the change in momentum by the change in t. We can also find the parallel component of dp dt by multiplying the magnitude of dp dt times p hat, or the unit vector of momentum. We can then find F net parallel, since we know that F net parallel and dp dt parallel are the same value. We can then calculate dp dt perpendicular by subtracting dp dt parallel from dp dt, and using this value to find F net perpendicular, since we know that they are the same. In addition to calculating the gravitational force acting on the star, we can also calculate the mass of the black hole using this force. We know the equation F gravitational equals the constant g times m1 times m2 divided by the distance between the two objects squared. Since we have all of the needed variables except for the mass of the black hole, we can solve for the mass of the black hole in this equation. We must first find the distance between the black hole and the star by using the magnitude of the position of the star minus the black hole. We can then find the mass of the black hole by solving for it from the gravitational force equation, where we get the mass of the black hole is equal to the magnitude of F net times the distance squared and divided by the constant g times the mass of the star. After we correctly modify the code, we can then run it and get a model of the star's motion. We can also see the components of the force acting on the star. The black arrow represents the parallel force acting on the star, while the blue arrow represents the perpendicular force, and the yellow arrow represents F net. We can also find the mass of the black hole over here in our values, as it is the last one printed. What does it mean? Throughout this lab, we have been using the knowledge that F net is the same value as dp dt. While they may be the same value, F net parallel, F net perpendicular, and F net are not exactly the same as dp dt parallel, dp dt perpendicular, and dp dt. This is because force is calculated using equations such as F equals ma or F equals mv squared over r. In contrast, dp/dt is an observed value, since it is the rate of change of momentum. What if the black hole whose mass you found was removed and a different black hole was placed in the same location? Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? To answer this, we must look back at the gravitational force equation. Since the motion of the star remains unchanged, we can assume that F gravitational has not changed. In order for this to be true, none of the constants on the right side of the equation can change, which means that we would not be able to tell the difference because the mass of the black hole would have to be the same. In conclusion, this lab has allowed us to explore the gravitational force equation as well as the relationship between dp/dt and force.